This lecture is on chapter 1.2 through 1.3. We're going to be talking about exact numbers versus measured numbers. What's the difference between those? And then this is going to get us ready for significant figures. We'll learn how to determine significant figures both from a regular form number, so 150 has how many significant figures, and from calculations. We'll also learn about scientific notation, which is exponential notation with significant figures thrown in. We'll learn about unit analyses, which is probably the most important thing we're going to learn all semester, which is a math technique where we essentially use our units to set up our problems for us. This is going to be very helpful for us. Okay, and then we're going to cover properties real quickly, and we'll talk about the property of density. We'll learn the calculations for density and how to end up using a given density term as a conversion factor. Okay, let's go ahead and begin. Let's review some of the past material, and we're asked to convert 0.0849 milliliters to microliters. Well, we have a calculation before us. We have one of two possible tools, equations or units, and we're using our units. Yes, we will formally learn how to do this in a little bit. But we've already seen this back in 1.1 through 1.2, and that was our first introduction to using our units. And you may recall, first, what is it that we're after? And write that down on the far right. That's step one. Then, what do we begin the calculation with? That's step 2, and we write that down on the far left. Now, we have to get out of that initial unit, so step 3 begins by placing that unit across the denominator line so that it cancels. Remember, anything that's divided by itself is 1 and essentially cancels. Now, we ask the big question, so getting this far should be pretty straightforward. Can we go straight from milliliters to microliters? No, we have to go through the base unit. So first from milliliters into liters, and then from liters I can go to any other prefix unit, including microliters. And concluding step 3, we have finished our setup. Do note all units cancel but the one that we're after. Now step 4 is to put in the numbers, and remember the base 10 number always goes where? With the base unit. So that would be the liters in this case. The other units, the millis, the nanos, the micros, the gigas, always get a 1. Remember, base 10 number goes with the base unit. The others, the prefix units, get 1. All right, and now 1 milliliter, like 1 milli anything, would be 10 to the negative third. Whereas 1 microliter, like 1 micro anything, is 10 to the negative 6. Okay, I have 3 significant figures in my original number. So 8.49 times 10 to something. My original number was 8.49 times 10 to the negative 2. And now I'm going to add the exponents for those numbers that are multiplied. So negative 2 plus negative 3 for negative 5. And then subtract the exponent for the one that's divided. And negative 5 minus negative 6, well, that's the same as negative 5 plus 6. And that's the same as 6 minus 5 for a positive 1. Next, we're asked to convert 4,712 kilobytes to megabytes. Well, we're still using our units, so still step 1, we're after megabytes. Remember, that's the capital M for mega. Step 2, we're going to start with that given number of kilobytes. And now step 3, we need to get out of that initial unit, so out of kilobytes. Here comes the big question, can we go straight from kilobytes to megabytes? No, we have to go through bytes, our base unit. Then from bytes we can go to megabytes or any other prefix unit. Now for the numbers, the base 10 number always goes where? With the base unit. So in this case that would be bytes. And then 1 kilobyte, like 1 kilo anything, is 10 to the third. Whereas a megabyte, like a mega anything, is 10 to the sixth. And you do eventually need to remember these numbers. Okay, so I have 4 significant figures in my original number, so I'm going to have 4 in my final answer. My original number was 4.712 times 10 to the positive 3. Now I'm going to take that 3 and add the other 3 to get 6. Subtract the 6 on the bottom to get 0. So 4.712 times 10 to the 0 megabytes. Next, what's the temperature in Celsius when it's 105 degrees F? Alright, well, we're still using our units. There's a little bit of a tweak to it, but step 1 is still the same. What are we after? Degrees C. Step 2 is still the same. We're starting with that 105 degrees F. Now step 3 is going to start by asking, is it time to add or subtract the 32 degrees F? And since we're in F, the answer is yes. So which is it, add or subtract? We pretend we're at the freezing point of water, which is 32 in degrees F, and we need to get it down to 0 in degrees C, and hence we're subtracting that 32 degrees F. Hit equals after doing the subtraction, and then out of degrees F and into degrees C, with 100 degrees C being the difference between freezing and boiling point of water, and 180 degrees F being that same difference. Put this on our calculator. Again, hit equals after you subtract the 32, and you should come up with 41 degrees C. Next, what is the temperature in Celsius when it's 235 kelvins? Again, we're using our units, and again, that begins with step 1. We're after degrees C. Then step 2, we're looking for a number with a single unit to start the calculation with. There's only one given, as is most of the cases. Normally there's only one number given with a single unit, so that has to be what we start with. Okay, so we're starting with the 235K. And now step 3, is it time to add or subtract the 273K? Yes, if you're in K, it's time to add or subtract the 273. Remember, we need to take into account the different starting points first. Or at least we would ask if it's time to do that. Okay, and is it add or subtract? Well, we go to the freezing point of water in K, which is 273, to get down to 0 in degrees C. We're subtracting that 273K. Now, out of K and into degrees C, they do have the same size temperature units, so most folks don't do that step. But if we're going to take care of our units, we're guaranteed they take care of us. Alright, and that gives us negative 38 degrees C. Can you have a negative temperature in C? Yes, just not in kelvins. Okay, on to new material, and we're going to discuss the differences between exact numbers and measured numbers. And when measured numbers come in, then we have significant figures. So we'll be talking about all this here right now. First, there are not too many examples of exact numbers. There tends to be only 2 instances. One are things that you count and can't be subdivided. So there is 6 people in my family. It can't be a fractional number, so that would be an example of an exact number. Then the relationship of 2 units within the same system gives us another example of exact numbers. So for example, there is exactly 60 minutes in an hour. There's exactly 12 inches in a foot. There's exactly 1,000 grams to a kilogram. Science is dominated by measurements. One of the things we do is a lot of experiments, and we want to be able to use numbers as many times as we can, so measured numbers are very common. And when we make a measurement, there's always a limitation to how well we've made that measurement. We can be limited by the tool we're using, we can be limited by our own skill, but there's always some limitation. And significant figures are a way of indicating how reliable those measurements are made. So when it comes to an exact number, we have an infinite number of significant figures, but when we have a measured number, we may only have 2 or 3. We'll see an example as to how many is appropriate here right now. Okay, we're given this red liquid and asked what is the volume of that red liquid. Let me blow this up. Now, we need to come up with our first digit. And which digit is that? Well, it looks like it's somewhere between 900 and 1000. And which is it closer to? And it looks to me a little closer to the 900. So my first digit is the 9 in 900. Now, if I just left my number as 900, that would tell my user there's just that one significant figure, that 9. Those 2 zeros are there just to tell us how big that number is. So for example, My mom lives 600 miles away. Now when I said that, did you think that she was right on 600, right between 599 and 601? You probably didn't. You probably thought that it meant she was close to 600 miles away. And so we find that we often use that in our normal language. And so when I would say that this volume is 900 milliliters, that would probably mean to most folks that it's pretty close to 900 milliliters. Now, when it comes to the significant figures, that one figure, ultimately that when I say that 9 and 900, it must be closer to the 9 and 900 versus the 8 and 800. So it has to be larger than 850. And it's closer to the 9 and 900 than the 10 and 1000, so it must be less than 950. So what you see here is that one significant figure, that 9, gives me a large 100 milliliter potential error range. It's saying to whatever my user is that the actual value is somewhere in this range. Okay, let's try to squeeze out another digit. And it looks pretty close to the 5 and 950. Okay, well, what would that mean if I said this volume has 950 milliliters? Well, I only see the two significant figures. That 0 is kind of a placement 0 to tell me how big the number was. And we'll talk about significant figures more here in a moment as far as regular form numbers. But anyway, that 950 must mean it's closer to 950 than 940 or 960. And so do note now we only have a 10 milliliter error range. It must be between 945 and 955. Let's try to sneak out one more. And actually it looks like it's midway between 940 and 950, so let's call that 945. Well, if I pass this on to a user, meaning here's the volume of this liquid and they go to use it, what are they going to interpret that to mean? Well, that it's closer to 945 than 944 or 946. So now I'm claiming that the error range is between 944.5 and 945.5. I'm down to a 1 milliliter possible variance. Well, that's really getting small. So is that actually an answer I should give? When I would give my final answer, meaning I'm going to put this label on the container or I'm going to tell the user this is the volume, how many significant figures should I use? Well, the 950 I have confidence in. The 900 I have confidence in. But the 945 I don't. I think I would just be lucky to have it fall within that range. And we don't believe in luck. We want to rely on certainty. And I'm quite certain it's between 945 and 955. So I'm going to go with two significant figures and call it 950. And if we look at what the author of this picture says, it's 946 milliliters, it would not have fit into that last example. It could not have been 945, but it does fit in within the error range that we get with 950. So first I want to point out this is what significant figures means. How accurately were those measurements made? Some can be made very accurately. We might get 4 or 5 or 6 significant figures, and some not so accurately. Like here, we only have 2. And volume is a classic example of not being able to measure very accurately. So that's ultimately what significant figures mean. Now, let's learn also how would you determine the number of significant figures when you're given a regular form number like that 950 or that 600. Well, we are going to assume that the zeros that are there telling you how big the number is, that's all that they're there for. And so we call those placement zeros. So again, if we have a 0 that's there just telling us how big the number is, it's not significant. And so that turns to be the zeros at the end of a large number and the zeros at the beginning of a small number. So in 2500, those two zeros I'm going to assume are only there to tell me how big the number was. So this number only has 2 significant figures, the 2 and the 5. Any non-zero digits are always significant. It's the zeros that we're not really sure if they're significant, so we assume that they're not. Again, if we have a small number, the zeros at the beginning would be considered placement zeros. So put your fingers over those zeros and then ask, can you tell how big the number is? And the answer is no. So we assume that that's all that they're doing. They're telling us how big the number is. So this number has 3 significant figures. The 0 at the beginning is tell us the decimal points coming up, and then those 2 zeros are placement zeros telling us how big the number was. Just like the 2 zeros at the end of 2500, we are going to assume are there just to tell us how big the number is. Now, if we have other zeros, we may find that they are significant. Not all zeros are insignificant. So in this number here, 0.000430, the first zeros are not significant. Put your thumb over it and ask, can you tell how big the number is? And your answer is no. That's what they're doing. So those aren't significant. Now what about that 0 at the end? Well, if you put your thumb over that and ask, can you tell how big the number is? Now you can tell how big it is. And so this 0 is significant. So we have 3 significant figures, and so this time a 0 was significant. I would also point out zeros between any non-zero digits would automatically be significant. Now, a generalization that works quite well is if you have zeros between the decimal point and the first non-zero digit, these are the ones telling you how big the number is and are not significant. Now, if you're not sure what I mean, how big the number is, I'm talking about in that 2500, we would write the number in scientific notation as 2.5 times 10 to something. If we can't tell what that something is, that's what I mean. That's telling us how big or how small the number is. What exponent would we have? And we'll be talking about that in just a bit. Okay, scientific notation is a way of illustrating numbers where essentially it's exponential notation, where we would take our first non-zero digit followed by the decimal point and the other digits all times 10 raised to some exponent. Now in science we have very large numbers and very small numbers, and so this is a very helpful technique. Now imagine you've already been introduced to exponential notation, so you probably have seen this before. Whereas 750 can be written as 7.50 times 10 to the second power. 10 to the second power is 100. 7.50 times 100, 750. Again, there are very large numbers in science. That first one is known as Avogadro's number. And then there are very small numbers in science as well. That second number is the water dissociation constant. Can you imagine keeping track of all those zeros when you're in the middle of an exam where you just simply don't have a lot of time? Well, I wouldn't want to do it even if I did have a lot of time. I'd much rather see the much more condensed 6.022 times 10 to the 23rd and the 1.0 times 10 to the negative 14. So that gives us one example as to why we need this. Okay, the procedure for writing a number in exponential notation, half of scientific notation, the other half is that it needs to have the correct number of significant figures. But first, we create our foundation where we take our first non-zero digit, followed by the decimal point, then any other digits that belong, all times 10. Then we need to determine what the exponent is. And if you've learned, if you move your decimal left, it's positive, right, it's negative, and I don't know if that's true because that doesn't make sense to me. What does make sense to me is if your number is larger than 1, your exponent is positive. And if your exponent is negative, if your number is less than 1, your exponent is negative. So note the negative on the water dissociation constant, K sub W, and the positive on Avogadro's number, N sub A. Bigger than 1 positive, smaller than 1 negative. To me, that makes a whole lot more sense than which way you move your decimal point. Okay, now we count how many places do we move the decimal point. And in the 750 we moved it twice, so that's where we got the 2. And the 6.022 times its 23rd, we moved it 23. And then 1 times 10 to the negative 14th, we moved it 14. Let's do a few of these. Okay, while we're at it, we're going to write our answer in full scientific notation, which means exponential notation with the correct number of significant figures. So when we have 4.50, our first question is how many significant figures do we have? And the question then is that 0 significant? Is it telling us how big the number is? No, which means it's there for another reason. It's actually known and hence it's significant. So step one, we write our base, our foundation. Then we determine the sign of the exponent. Well, the number is bigger than 1, so our exponent is going to be positive. And we didn't move the decimal at all. So 4.50 times 10 to the 0. 4.50, that's not scientific notation. 4.50 times 10 to the 0 is, and remember, anything to the 0 power is 1. Okay, 1.25 million. How many significant figures do we have? Are those zeros significant? No, they're placement zeros. They're just to tell you how big or small the number is. So there's our foundation, 1.25 times 10. Then our number is larger than 1, so the sign of our exponent is positive. And we moved our decimal over 6 places. So 1.25 times 10 to the 6. What's 10 to the 6? 1 million. What did I call that number earlier? 1.25 million. Next we have 50. How many significant figures is in 50? The 5, just the 1. There's our foundation. Sign of our exponent, positive, and we moved our decimal over 1. Next we have 0.001050. How many significant figures do we have here? We actually have 4. The 1, the O, the 5, and the O. Those first zeros are placement zeros telling us how big the number is. The others aren't telling us how big the number is. What are they telling us? They're telling us this number is known. Okay, there's our foundation, and what's the sign of our exponent this time? That's right, it's negative. A number smaller than 1, the exponent is negative. And then we're moving our decimal point over 3 places. We already determined that it's negative, so we get the negative 3. Okay, we just learned how to determine the number of significant figures when we're converting a regular form number. What about if we have a calculation, which is going to be a very common thing? Okay, well, first we have 2 different methods of determining significant figures, one for multiplication and division, and then another for addition and subtraction. I will say that the vast majority of calculations in science involve multiplication and division. Not too many with addition and subtraction, though there are some. Okay, well, first let's think about this. My final answer really can't be more accurate than the least accurate number that I use in it. So what that means is your final answer will have the same number of significant figures as the number that had the fewest. So if I have the distance of 240 miles and I divide it by 40.00 hours, well, that 240 miles has 2 significant figures while the 40.00 hours has 4. So when I give my final answer, it should have 2. This is illustrating 6 with 2 significant figures. For addition and subtraction, it's actually a bit different, but it still should make a lot of sense. We ultimately are going to give our answer to the digit that's known for all of the numbers. So let's take these 3 numbers, 1000.0, 0.010, and 100.0000, and add them together. And we'll do so longhand like we did when we first learned to add numbers together. Now, I'm not going to give all of those digits. Where am I going to stop? I'm going to stop at the digit that's known for everybody. And do note that tens place is the last digit that's known for the 1000.0. Just think of the hundreds place, the next digit, as being a question mark. Maybe it's a 1, maybe it's a 2. Well, if I don't know it in the original number, I surely don't know it in my final answer. So that's why I would round to the tenths place, because that was the digit that was known for everybody. I would point out, multiplication and division versus addition and subtraction, quite different. Don't confuse the two. Okay, now on to unit analyses, sometimes called dimensional analyses or the factor label method. I believe this is the most important tool I'm going to give you all semester. This is a technique where we essentially use our units to set up our calculations for us. Almost all science problems and real-life problems have units, and we're going to learn to use those units to set up our problems for us. That means we don't need to remember equations, we don't need to isolate variables. This hopefully will be a very easy tool for us. Now the first time you use it, it won't be easy because nothing is easy the first time. But one of the wonderful things about unit analyses is it's always the same 4 steps. And because of that, we're going to get a lot of practice doing the same things over and over and over. So that when we might get to something you might think as more complicated chemistry, math type stuff, well, if we can use our units, it's going to remain easy for us. Okay, well, this example here illustrates how if we went 75 miles an hour for 2 hours, we went 150 miles. Note how the hours canceled and gave us miles. Well, let's actually go through the tools, which are called conversion factors, and that 75 miles per hour is a conversion factor. The relationship of one unit to another is a conversion factor. So 7 days per week would be a conversion factor. 1,000 milliliters per liter would be a conversion factor. 75 miles per hour is a conversion factor. 1 unit per another is a conversion factor. And that's our primary tools. Okay, now let's learn the procedure, and you've already heard me say step 1. What are you after? Well, that's step 1 in our unit analysis procedure. What are you after? And write it down on your far right. I mean, what units are you after? Does your final answer need the units of milligrams? Does it need miles? What is it? Write that down on the far right. Now we do this for 2 reasons. First is it gives you a clear target so you don't get lost, and believe me, I've seen people get lost. The other is it tells us all about step 2. If we finish with a single unit, which is what we do most of the time, that means we're starting with a number with a single unit. And so for step 2, we would identify that and write it down on the far left. Now what if you're after 2 units, like miles over hours? Well, then you would start with 2 units, like meters over seconds. You might, if you're going to be doing physics, have more than 2 units. In this class you'll have 1 or 2. Essentially it would still be the same thing. If you finish with 4, you would start with 4. Okay, on to step 3, which also begins fairly easily. We have to get out of our initial unit, so place it across the denominator line so it cancels. Remember, anything divided by itself is 1 and hence cancels. Then we would ask, can I go from this unit to my final answers unit? And if the answer is yes, then you've got 1 conversion factor and you would be done setting it up. But if not, you might have a second or a third conversion factor that you have to use. We'll do some examples in a moment. I recommend that we wait till step 4, the very end, to put in the numbers. The reason for this is we don't want to be thinking about the numbers. The numbers will fool you, the units will not. So we should be thinking completely about the units. Once we have the numbers in, multiply the tops, divide the bottoms. Okay, let's do an example. We're asked how many seconds are in 10 years. So for some reason we need to know how many seconds are in 10 years. Well, we're using our units. So step 1, we're after seconds. That tells me everything I need to know about step 2. I'm going to start with that 10 years. Most of the time there's only 1 number with a single unit given. It's going to be what you start with. Step 3 begins by getting out of that initial unit, so out of years. Getting this far should be pretty straightforward. Step 1 should be easy, step 2 should be easy, and the beginning of step 3, well, it can't get any easier than that. Now will come the big question. Can you go straight from years to seconds? Do you know how many seconds are in a year? I don't, so I'm going to get myself closer to seconds from years. What takes me closer to seconds from years? And I think days. Now I don't want to go with months because there's not always the same number of days in months. So that's why I'm going to first go to days. I know how many days are in a year. Okay, if I was after days, I'd be done. But I'm not after days, so I do the same thing. Place it across the denominator line. Then, can I go to seconds from days? No. So what's going to get me closer? Hours. Okay, if I was after how many hours are in a year, I'd be done. But I'm not, so let's get out of hours. Can I go to seconds now? No. I know where I'm going though, minutes. And if I was after minutes, I'd be done, but I'm not after minutes, so can I go from minutes to seconds? And this time the answer is yes. And note how all of those units cancel, but the one that you're after, I would recommend that we get in the habit of scratching out those units that cancel and circle what's left. That would just make it jump out that much more if we have made a mistake or when we get the right answer. Now for the numbers, and if you weren't expected to know these numbers, they would have been given to you in the problem. But I expect you know all of these numbers. And now 10 times 365 times 24 times 60 times 60. If I had other numbers besides ones, I would divide those, divide 1, divide 1, divide 1, divide 1. Of course, we don't do the ones. And that would be 315 million seconds in those 10 years. There's our 4 steps. Now, let me quickly review our 4 steps. Step 1, what were we after? Seconds. Step 2, what did we begin with? The 10 years. Step 3 began by getting out of years. Years took us into days. Then we had to get out of days. Are you seeing how each step prepares you for the next? That's why we don't want to jump over steps. If you're jumping over steps, you're essentially leaving yourself without these little clues. From days to hours, then out of hours, from hours to minutes, then out of minutes, and then finally we went into seconds, and lastly put in the numbers and push the buttons on our calculator. But do note how each step prepared you for the next. This is what's going to keep this from becoming hard or complicated. 4 simple steps where each one prepares you for the next. Don't ever try to jump straight to step 3 or step 4. Okay, let's do some more, and I've chosen some real-life problems. How many miles will you have driven if you drive 1.25 miles per hour for 0.75 hours? I chose this problem because I know some people are already trying to do this in their head. So 1.25 divided by 0.75, or 0.75 divided by 1.25, or are you multiplying them? Well, no matter which of those you think it is, are you sure? And that's one thing you don't get when you do it in your head. But when you use your units, you can be sure. So step 1, we're after miles. Step 2, well, only one of these numbers has a single unit attached to it. That 1.25 miles per hour is a conversion factor. Can't start with 2 units if you finish with 1. So the 0.75 hours is what you start with. And now step 3, let's get out of hours. Can we go straight to miles? And we can see that conversion factor sitting right there in front of us saying, yes, we can. Sometimes that's a really good technique or procedure to pull out those conversion factors as a preliminary step so that they're sitting right there in front of you. And it also makes it clear where the numbers go. The 1.25 with the miles, or 0.9375 miles. Now, how many significant figures should our answer have? 2. Next, how far can you drive on $50 of gas? Is there enough information in this problem? No, we need to know our mileage and the cost of gas. Okay, so gas costs $1.89.9 per gallon, and my car gets 35 miles per gallon and has a 15-gallon tank. In this problem, I actually am giving you a piece of information you don't need. This is the only time this whole semester you're going to get a piece of information you don't need. But real-life problems, you might have information that you don't need and you're not sure you need it or not. Okay, well, we are still using our units. So what are we after? How far? Miles. Step 2, well, one of these numbers has a single unit attached to it. So is that just $50 or $50 per something? I think that's just $50. Is that $1.899 or $1.899 per something per gallon? So there's 2 units. We're not starting with that. And is that 35 miles or 35 miles per something per gallon? And is that 15 gallons or 15 gallons per something That's just 15 gallons. Okay, so we have two numbers with a single unit, the $50 and the 15 gallons. Which do you think is ultimately going to determine how far you can get down the road? And I would say that as long as you have a big enough gas tank to get to the next gas station, the size of your gas tank isn't going to matter. So it's the $50. All right, step one, step two, and now the beginning of step three. Let's get out of dollars. Here comes the big question. Can we go straight from dollars to miles? No, so as we look up in the problem, we see dollars will take us to gallons. Okay, so into gallons. We're not after gallons, so let's place it across the denominator so that it cancels. Can we go straight from gallons to miles? Yes, we know that association, and so we're done. For the numbers, that was $1.899 per gallon and 35 miles per gallon. So 50 times 35 divide the 1.899, and my answer is 920 miles, or 9.2 times 10 to the 2, so that I can make it clear that this answer only has two significant figures. The 35 miles per gallon is the two significant figures. Do note, the $50 is an exact number. That is something you can count. Okay, another example. My puppy walked 106 yards in 1 minute. How fast does he walk in miles per hour? I did this problem because now we're going to have a dual unit answer, somebody per somebody else. What happens when you have one unit over another for your final answer? Well, then you're going to have one unit over another for your starting material. Either you already have an existing dual unit like meters per second, or you have two separate pieces of information like we have here. So we have yards and minutes. Which do you think goes in the top and takes us to miles? Well, yards and miles are both distance units, so I think yards goes in the top. If you ever get stuck with the top, ask about the bottom between yards and minutes, which is going to take us to hours. That's right, minutes. Minutes and hours are both time units. All right, we need to get out of both these units, so let's take care of our denominator, or excuse me, our numerator first. So out of yards, that's supposed to be a D, not an R. So out of yards, can we go straight to miles from yards? I don't know how many yards are in a mile. I only know how to get to miles from feet. So where do you think I need to go first? Into feet. So this is an example. Sometimes I have to look down the road to see how am I going to get there. Now that I'm in feet, I can go 2 miles. And that YR should be YD. All right. Scratch out yards, scratch out feet, circle miles, and that makes it jump out. I need to get out of minutes still, so let's put that on the top. Can I go straight from minutes to hours? And we most certainly can. Scratching out minutes and circling hours, I have miles and hours circled. I have confidence I've done this correctly. All right, I think you know there are 3 feet in a yard, 5,280 feet in a mile. Actually, I didn't know that when I first got the chemistry, but I quickly learned. And of course, we all know 60 minutes in an hour. And putting this on my calculator, I come up with 3.61 miles per hour. So again, if you have one unit over another, then for step 2, throw out a denominator line. And we're going to look for one unit over another to start with. Okay, on to properties. And first, a property is some characteristic of your subject that we can use to recognize it when we see it again. Now, we tend to have 2 types of properties, chemical properties and physical properties, and all chemical properties involve a change. So there's your key word, a change. So when you light a piece of paper on fire, what you have at the end is not what you began with. It changed. So here's some examples. Burning of paper, decomposition, and corrosion. We had changes. Changes down at the atomic/molecular level. When we have physical properties, these often can be witnessed without any type of change. Things such as color would be an example of physical property. Anything with a number, like my weight and my height, those would be examples of physical properties. Now, sometimes I can fool you by asking the melting point of water, where it changes from a liquid to a solid, is 0 degrees C. Is that a chemical change because I mentioned change? No, that would actually be a physical property. It's still water. We just change it from a solid to a liquid. We also have physical quantities. Essentially anything with a number attached to it would be a physical quantity. Anything with a number attached to it, really you shouldn't expect to be a chemical property. Okay, one physical property is solubility. How much of one chemical you can dissolve in another. Well, let me just go ahead and define solubility, and essentially this would be the amount of a solute, which you're dissolving, that can dissolve in a given amount of a solvent. Now we have to say in so much solvent because if I increase my solvent, it should make sense we can increase the amount that can dissolve. And this is usually stated under conditions of temperature. Why would temperature be mentioned? Because temperature can affect your solubility, and we'll find out why as we progress through this course. Another physical property is the electromagnetic absorption spectrum and the electromagnetic emission spectrum. And so these are different wavelengths that of light that are absorbed or emitted. And actually the electromagnetic spectrum goes all the way from radio waves up through gamma rays. Okay, a lot of things are colored because they're either absorbing or emitting in the visible portion of the electromagnetic spectrum, which is from roughly 400 to 700 nanometers. And we'll learn more about light and the electromagnetic spectrum also at a later time. Okay, density is also a physical property, and when I talk about density, I like to begin by talking about things floating or sinking. For something to float, it must have a density less than that than the liquid or the fluid that it's floating in. Let me quickly talk about liquid fluid. What's a fluid? Well, a fluid actually is anything that doesn't have a defined shape. So both liquids and gases are fluids. Okay, so hot air balloons float in the atmosphere, so that fluid actually would be a gas. Alright, so here we see that the cork and the ice cube are floating, so they have densities less than water, and the cork is floating way higher than the ice cube, so that would tell us that the cork is much less dense than the water, and the ice cube just a little bit less dense. What about those two objects on the bottom, those two metals? Well, they have densities greater than water, hence they have sunk. Now, ultimately, density is the ratio of your subject's mass to its volume, so mass over volume. But we're going to do our calculations using our units. Let me get to that in a moment. This is showing how we would be measuring the mass of a subject over here on the left part of the picture, and then how we would measure the volume. We're actually going to be doing this in the lab here fairly soon, and so we're going to see that we started with a known volume of liquid in that graduated cylinder and then added our metal cylinder carefully down into it, and the volume went up. That increase in volume would be the volume of that solid. Take the mass, put it over the volume, and that would give us the density of that metal bar. Now, when it comes to density, our three different phases have their own units. For a solid, we use the units of grams per cubic centimeter. A cc is a cubic centimeter. Now, I point out that a cc is exactly the same as 1 milliliter. Because of the way that the metric system was designed, it is exact. 1 cc is exactly 1 milliliter. So if you know how to get the milliliters, you know how to get the cc's. Okay, so gram per cc for a solid, gram per milliliter for a liquid, and grams per liter, a much bigger volume, for the much less dense gases. So if I want to know the density of a gas, I'm going to set the equation equal to grams per liter. And remember, we're going to be using our units, so we need to remember these units. Okay, just as an example, if we're after the density of whatever, we'll determine is it grams per cc, grams per milliliter, grams per liter for step 1, and set our setup equal to that. You remember step 1. Let's go ahead and do an example. Okay, what is the density of an unknown metal that displaces 1.17 liters? There's our volume and has a mass of 16.82 kilograms. Well, first, an unknown metal, what phase of matter do you think this is? A solid, a liquid, or a gas? I would assume a solid. So we're after grams per cc. Then step 2, well, if you're finishing with one unit over another, then for step 2 you're starting with one unit over another. And so between liters and kilograms, which goes on top and takes us to grams? Kilograms. Between liters and kilograms, which goes on the bottom and takes us to cc? Liters. Kilograms and grams are both mass units, liters and cc's are both volume units. Okay, we need to get out of both, so first, out of kilograms. Now, can I go straight from kilograms to grams? Yes, I certainly can, and my numerator is taken care of. Scratch out the kilograms and circle the grams. And now liters needs to be canceled, so let's place that on the top. Can we go straight from liters to cc? And this probably depends on you. Do you want to go straight there, or do you want to go through milliliters? Let me do an extra step and make it a little bit easier and go to milliliters first, and then from milliliters we can go to cc. For the numbers, base 10 numbers, still going with the base unit, 1 kilogram, 10 to the positive third grams, and 1 milliliter, 10 to the negative third liters. Base 10 number, always going with the base unit. And then 1 cc is 1 milliliter. And because they were the same, you might have just simply put 1 cc underneath the 10 to the negative third liters. If you're comfortable doing that, nothing at all wrong with that. If you're not comfortable, then just do this little extra work and keep yourself comfortable. And I come up with 14.4 grams per cubic centimeter, giving my answer to 3 significant figures, which is appropriate for the 2 numbers that were given, one with 3, one with 4. Now, if we're given a density term, we're actually being given a conversion factor. Just like if I give you the velocity of 75 miles an hour, that can act as a conversion factor between miles and hours. If I give you the density term grams per liter, that can act as a conversion factor between grams and liters, meaning between mass and volume. Okay, let me just illustrate that if you have grams per milliliter, so for example, I have a liquid with a density of 3.82 grams per milliliter. It gives me the conversion factor of 3.82 grams over 1 milliliter, or 1 milliliter over the 3.82 grams. And we'll know which one to use when we get there. So we don't have to worry ahead of time which one are you using. Remember, our units tell us what's next. Let's do an example. How many kilograms does 3.618 liters sample of alcohol weigh if it has a density of 0.772 grams per milliliter? Okay, we are using our units, so step 1, we are after kilograms. Step 2, only one of those numbers has a single unit attached to it, and that would be the liters. That grams per milliliter, 2 units. Can't use 2 if you can't begin with 2 if you finish with 1. We just exchange units. We don't just mysteriously come into them or mysteriously get rid of them. So that's why we would start with the same number of units that we finish with. And now, step 3, out of liters. And I hope you found step 1 equals kilograms. Step 2, start with 3.618 liters. And the beginning of step 3, put out a denominator line and liters on the bottom. I hope you found that to be very easy, very straightforward. Now comes the big question. Can we go straight from liters to kilograms? And immediately we realize we're in volume and we're trying to go to mass. Can we do that? Only if a density term is given. And the density term is between grams and milliliters. So first we need to be in milliliters. Then from milliliters we can go to grams. And at this point we're in mass, which is what we want. So one more conversion from grams to kilograms. Note all units cancel but the one we're after. For the numbers, base 10 number still going with the base unit. .77 goes with the grams. 0.772 goes with the grams. And again, base 10 number goes with the base unit. And that would then be 2.79 kilograms. Okay, let's practice some of the things that we've just learned. First, the oldest known flower lived 120 million years ago. Is this an exact number or a measured number? If you're tempted to say it's an exact number, I would ask you, is it 120 million years now or now? Because it couldn't be both if it was exact. There's 1,000 milliliters in 1 liter. Is that exact? Yes, it is. That's 2 units in the same system. So those relate through exact relationships. What about there being 454 grams to a pound? No, that's measured. Those are 2 different systems, the metric system and the English system. One system isn't based on the other, so they took a pound and measured it. How many significant figures do you have in 123.0? And the question, of course, is that 0 significant? Yes. Is it there to tell you how big the number is? No. I put my thumb over it and I can still tell how big the number is. So why is it there? Because it's known. What about the 2 zeros in 100? Are those significant? Let me put my thumb over it. Now I can't tell how big it is. That's one significant figure. Those 2 zeros are not significant. And what about in 102,030,000? The 4 zeros at the end are not significant. Those are placement zeros, and we're assuming they are just there to tell us how big the number is. And now you may see the downside of regular form numbers. Maybe I do know those zeros. Well, if I put it in regular form, it's not illustrated. Okay, and in 0.00010, we have how many significant figures? 2. The first zeros are not significant, the one at the end is. So 4 significant figures for 123.0, 1 for the 100, 5 for the 102,030,000, and 2 for the 0.00010. Now, how would you write 123 in scientific notation? Well, first we create our foundation. So we take the 1, followed by a decimal point, and a 2 and a 3 times 10. There's our foundation. I hope you find that nice and easy. Then we determine the exponent, beginning with the sign, and the sign would be positive. And we move the decimal place 2 for a positive 2. What about 0.001234? Well, we would start with the 1, put a decimal point, the 2, the 3, the 4 times 10. And this time with the number being less than 1 tells us the exponent is negative. And then we count over 1, 2, 3 places we moved it. Okay, another real-life problem. What's the maximum number of friends that can be fed pizza if each friend eats 5 slices and you only have $50? At the pizzeria you selected, each pizza costs $12 and has 8 slices. Well, I don't have a big book of real-life equations to look this up, but I do have my units. And that begins with step 1. Equals friends. Step 2. I'm looking for a number with a single unit to start the calculation with. So, is that just 5 slices or 5 slices per something? Per friend. Is that just $50 or $50 per something? I think that's just $50, so I'm pretty sure we're going to start with that. And is that $12 or $12 per something? Per pizza? And is that 8 slices or 8 slices per something? Again, per pizza. So, only the $50 had a single unit. So it was obvious what we were starting with. And now let's go on to step 3 and get out of dollars. Can we go straight from dollars to friends? Nope, and having color sure helps. Looks like dollars is going to take us to pizzas. Now, if you're wondering or worrying that maybe this is not the right direction, I've been waiting for over 20 years for my units to take me in the wrong direction, and it's yet to happen. So be confident that, yep, we're going in the right direction. All right, let's get out of pizzas. Can we go to friends now? No, let me see, what else do I have with pizza? Slices. Oh, into slices. Not after slices. So, again, out of that unit. Can we go from slices to friends? Yes, we do have that association, and so we are done. Putting in the numbers for step 4. Actually, before we do, let's scratch out the dollars, scratch out the pizzas, scratch out the slices, and circle the friends, just to make sure that everybody has canceled. I can't tell you how often folks don't do the scratching and are left with a unit that is not correct. Okay, that was $12 per pizza, 8 slices per pizza, and 5 slices per friend. And I come up with 6.67 friends. I don't have fractional friends, so how many friends should I take? 6, that's right. I want to make sure we have enough to feed everybody. Okay, one more real-life problem, and I'm using real-life problems to illustrate units work with any set of unit analyses, works with any set of units, and real life has lots of units, but not so many equations. All right, anyway, we're asked how many 24-ounce cans of tomato sauce. You need to make enchiladas for a party of 34 people. You plan for each person to eat 3 enchiladas, and the recipe makes 12 enchiladas from 16 ounces of sauce. All right, what are we after? Cans of sauce. Step 2, which number has a single unit? Is that just 24 ounces or 24 ounces per something? Per can. Is that 34 people or 34 people per something? I think that's just 34 people. And is that 3 enchiladas or 3 enchiladas per something? Per person. And is that 12 enchiladas or 12 enchiladas per something? Per 16 ounces of sauce. So only the 34 people had a single unit, so by default it must be what we start with. We don't have to scratch the head and wonder. On to step 3, let's get out of people. Can we go straight from people to cans? No, as we look up and see people's going to take us to enchiladas. Then out of enchiladas. And enchiladas takes us to ounces of sauce. Then out of ounces of sauce. And ounces of sauce can take us to cans. And we are done. Again, pulling out those conversion factors and putting them right there where you can see them can sometimes make this a whole lot easier. Now for the numbers, and it also tells you for sure where the numbers are. 3 enchiladas per people. 24 ounces, 16 ounces per 16 ounces of sauce per 16 ounces of sauce per 12 enchiladas, and 1 count per 24 ounces of sauce. And that would then be 5.67 cans. Well, I don't know anywhere they sell 0.67 cans, so how many cans should I buy? 6. I want to make sure I have enough. Okay, here's another metric conversion, and now we've been fully versed in unit analyses in our 4-step procedure. Beginning with step 1, we're after micrometers, which tells us what we need to know about step 2. We're starting with 37,400 nanometers. And now step 3, let's get out of nanometers. Can we go straight from nanometers to micrometers? No. Not the way that I'm teaching this. We need to go through the base unit, so into meters. Why do we go into the base unit? Because it relates to everybody, so we're guaranteed we can get into it, and we're guaranteed it'll take us to any other prefix unit. And if you're trying to go straight from nanometers to micrometers, you're just saving yourself one conversion factor, and you're going to put a lot more of a burden on the brain. Okay, now for the numbers. The base 10 number always goes where? With the base unit. So the meters get the tens, the nanos, the micros, the millis, the kilos always get a 1. And then 1 nanometer, like 1 nano anything, would be 10 to the negative 9th. Whereas 1 micrometer, like 1 micro anything, is 10 to the negative 6th. Okay, I have 3 significant figures in my original numbers, so I'm going to have 3 in my final answer. You can just put this on your calculator or do as I do. My original number is 3.74 times 10 to the 4. 4 plus negative 9 is negative 5. Negative 5 minus negative 6 gives us positive 1. One more. We're asked to convert so many kilograms to milligrams. We are still using our units. Step 1, we're after milligrams. Step 2, I think it's obvious. We're starting with that 0.0072 kilograms. And we know how step 3 begins. And now comes the big question. Can we go straight from kilograms to milligrams? No, we're going to go through grams, our base unit, to get there. So first into grams, and then to milligrams. And that'll make our lives a lot easier. For the numbers, base 10 number, still going with the base unit. And a kilo is 10 to the positive 3rd. And a milli is 10 to the negative 3rd. You can put this on your calculator or do as I've been doing. 0.0072 is 7.2 times 10 to the negative 3. Negative 3 plus positive 3 is 0. Then 0 minus negative 3, well, that of course brings us back to positive 3. How many deciliters does a 162 milligram sample of gas occupy if it has a density of 1.14 grams per liter? We're still using our units. Eventually we'll have some equations, but we're still using our units. And that begins with step 1. What are we after? We were specifically asked for deciliters. Then step 2, what are we starting with? Well, that 1.14 grams per liter has 2 units. Can you start with 2 if you finish with 1? No. So it must be the 162 milligrams. And now step 3, let's get out of milligrams. And now, can we go straight from milligrams to deciliters? Hold on, milligrams, that's mass, deciliters, that's volume. Can we do that? With a density term we can. And so how am I going to get to volume? From the mass unit of grams. That'll take me to the volume unit of liters. So first into grams, which happened to have been my normal first step anyway, when I didn't start in a base unit. Then out of grams and into liters. And you gotta love it that we're in liters, because being the base unit, we're only one move away from deciliters. Base 10 numbers, still going with the base units. And that 1.14 is going to go with the grams. It doesn't matter if it's on the top or on the bottom. Numbers go with specific units. It's never that this number is always on the top or on the bottom. So 162 times 10 to the negative 3rd, divide 1.14, divide 10 to the negative 1. Do make sure you know how to put these numbers on your calculator. and I come up with 1.42 deciliters when you put that in scientific notation. Okay, that concludes today's lecture, and we began with exact numbers versus measured numbers. Not too many examples of exact numbers, lots and lots of measured numbers. And when it comes to measured numbers, significant figures are a way of telling the user how well were those measurements known. We know how to determine significant figures from a regular form number, and we also learn how to determine the number of significant figures when they're involved in a calculation. We learned our most important tool for the semester here in unit analyses, a method of using our units to set up our calculations for us. And then we talked about some properties, chemical properties and physical properties, and then we learned about density and their calculations.